Chapter 20, slides 1 through 5. In this chapter, we're going to be doing chemistry on carbonyls. And the specific carbonyls we're going to focus on include the carboxylic acids, esters, amides, and acid chlorides or acid halides. What I have here is a chart of a bunch of different carbonyls. And remember, carbonyls are the carbon double bond oxygen. And so what's interesting about the functional groups that we're going to be looking at is that they all have a carbon double bond oxygen in it. And just for comparison's sake, I've put a methyl group on the left-hand side of each one of these carbonyls. So, what makes an acid halide an acid halide is the fact that it has this chlorine group or bromine group off of the carbonyl. An aldehyde has a hydrogen off the carbonyl. A ketone is flanked by two carbon groups. So it's got a carbon on the left, in which case I have a methyl, and on the right I added another R group, another carbon-based group. So that's a ketone. A carboxylic acid has an OH on one side, an ester has an OR, another O carbon group, and an amide has a nitrogen in some substitution pattern. It could be hydrogens, it could be carbons off of it. So these are the functional groups we're going to be looking at, and the way that we're going to be looking at these functional groups is from the reactivity standpoint. I'm going to put a Q here, of the carbonyl being electropositive. So what does that mean? It means that the carbonyl carbon is an electrophile. The way this functions most often is that a nucleophile of some variety will be attracted to the carbon that's partially positive. Okay, so this is the trend that we're going to see. As you'll notice at the top here, I have a question for you. How do these carbonyls compare in reactivity? Okay, well, if I have a carbon, right, that is partially positive, I'm going to represent how electropositive something is by giving it a larger blue circle. Okay, so what that means is that carbon is really electropositive. If I give a carbon a small circle, I'm going to say that that is less electropositive. Which carbon would be a better electrophile? Is it better if it's more positive or less positive? Well, the answer is the more positive something is, the better the electrophile it is. Just like we saw in the previous chapters with SN1 and SN2, a strong nucleophile was one that is negative. A weak nucleophile is something that's just partially negative, right? So the same goes for an electrophile. Yes, if a carbon is absolutely carbon plus, a carbocation, that is a fantastic electrophile. But there are variations or gradients of how electropositive a carbonyl can be. So let's take a look. The only thing that's different going from acid halides to amides is the group in green that I've highlighted. Let's say that the X is a chlorine, like an acid chloride. Well, acid chlorides are electron withdrawing groups because they're extremely electronegative. So what you're doing is you're really pulling, you're teasing the electron density from the carbon it's attached to. The chlorine's winning, right? The chlorine has most of that electron density. That means that the carbonyl carbon is pretty darn electropositive. Understand that the carbonyl itself, the oxygen, is also, with a double vector dipole there, pulling electron density towards the oxygen. So if the chlorine's also pulling electron density towards it, then you're really stripping that carbon of electron density, making it very electropositive. So the most reactive carbon of all of these carbonyls is the acid chloride. In fact, your nucleophile doesn't even need to be full-on negative to attack an acid chloride. Okay, let's look at an aldehyde. what's the group hydrogen doing? Absolutely nothing. Hydrogens are neither electron donating nor are they electron withdrawing. They're really just there to make you feel like you have your octet, right? They're placeholders in a sense. They're an atom that can share 2 electrons with you, but the nature of the atom itself is neither donating or withdrawing electron density. All right, what if we switch gears here? Now we've turned a corner. We went from electron withdrawing to neither electron withdrawing to electron or electron donating to, what if I have a ketone where R is another methyl or ethyl group, which is electron donating by induction? Yes, the carbonyl is withdrawing, but now I've switched from another withdrawing group, chlorine, to a donating group, like a methyl. So by induction, it's mildly electron donating. That's going to make the carbonyl less electropositive. So the biggest electropositive group is the acid chloride, followed by the aldehyde. I make that a little bit smaller. I'm going to make this a little bit smaller. In fact, if I made an acid halide or bought an acid halide from a company, I'd probably, once I open the bottle, I would use it immediately. They're super reactive, even with the moisture in the air. If I made an aldehyde, I'd probably keep my product in the freezer or the fridge just to keep the reactivity down, because again, it could react with lots of stuff. Ketones, much more stable because the carbonyl is not as electropositive, so it's not as susceptible to be attacked. And then let's move one more over. Let's look at the carboxylic acid. Well, inductively, the OH group is donating, but even better than donating by induction is donating by resonance. The oxygen has lone pairs, which can pi donate. So you've got an electron donating group with the OH attached to the carbonyl, and this is by pi donation. Same goes for the ester. You have an oxygen, which, yep, is electron donating, but better than that is the fact that it can actually, through resonance, pi donate, right? And by resonance, the electrons can go up. But I just wanted to show you that it's a pi donating group. So it might not be surprising that the reactivity of a carboxylic acid and an ester are actually about the same. And a ketone is more reactive than both of those. So we've decreased that electrophilicity again. Still electropositive, it's just diminishing. Lastly, we have the nitrogen, and the nitrogen is also a pi donor, but I've switched to nitrogen right? It's electron donating. Nitrogen, when compared to oxygen, is less electronegative. Remember, that means less greedy. So it's more willing to donate its pi system. So it's a better pi donor, more willing to donate. So that really depletes the electropositivity of our carbon. And this is like a little dot. So amides are the least reactive of all. Doesn't mean we can't do chemistry with them. It just means that they're the least reactive of all of these carbonyls. Which, if you think about it, amides are what proteins are made out of. The bond between the carbonyl and the nitrogen is the peptide bond in an amino acid sequence. So if those bonds are the peptide bonds, and that's what holds a whole protein together, then the reactivity of that carbonyl, it's good in nature that carbonyl is not super reactive with everything. Otherwise our proteins would be falling apart and dissociating all the time. Okay, so we're going to be using these carbonyls as electrophiles, and we're going to be introducing different nucleophiles. I want you to pay attention to the aldehyde and the ketone, because they're a little different in the sequence that we've written out, right? In the sequence that we've written out, ketones and aldehydes are their own functional group that have their own special chemistry. Thus, we have a completely set aside chapter for aldehydes and ketones. So I'm not going to really be talking about aldehydes and ketones as the starting material in this chapter. We're going to concentrate on the types of carbonyls that have something other than carbon or hydrogen on one side. Why is this the case? Well, if you think about it, we defined in the SN1, SN2, E1, E2 chapter what a good leaving group was. Okay, did we see carbon minus as a good leaving group? No. Did we see hydrogen minus as a good leaving group? No. So what we did see are things like chlorine, right? And what I'm going to introduce is that under the right conditions, we can get an O minus or an NR2 minus, or better yet, water. We saw water as a good leaving group, or a neutral alcohol, right? Or a neutral amine. And we definitely saw chlorine and things like bromine as good leaving groups. And we figured this out. I mean, we've seen these trends before when we looked at REO. REO is the process that we can use to determine when an atom leaves with extra electrons, how stable is it? What you'll notice is that in green, I've highlighted a group that could potentially leave, whether it left as an O minus or a neutral species. It is going to be a system that has the potential to leave. The aldehyde and the ketone have nothing but carbons and hydrogens flanking its left and right side. Thus, it's not going to have any potential leaving group. So its behavior, how they function, are a bit different. And we group them together because they have similarities. We group them together in their own chapter. So this chapter is going to be focused on carbonyls that have a group on one side of them that we can move off. I've tagged these groups as Q, right? So what we're going to see is a nucleophile attacking a carbonyl. The electrons go in and up. Notice the name, in up, right? The electrons form a bond with the carbonyl, and then the pi bond breaks and those electrons go up into the oxygen, and we form an intermediate. Notice that the carbon that we started with was sp2 hybridized. It was an sp2 trigonal planar carbon. So the nucleophile could come in from the front, it could come in from the back. And once it bonds, once the nucleophile forms a bond with the carbon, notice that that carbon is now sp3 hybridized. It's an sp3 hybridized carbon, so this intermediate. It's at this intermediate stage where we've got to analyze what kind of groups we have off of our carbon. If Q is something that is not carbon or hydrogen, right? One of the green ones, if it's an OH or an OR or an NR2 or a chlorine. So if it is not a carbon or a hydrogen, then the electrons can come right back down and kick off that leaving group. And now what we've done is we have replaced Q with whatever the nucleophile is. So we started with a carbonyl, we ended with a carbonyl. Okay? If we end with a carbonyl, it means we still have a carbon that's electropositive, and maybe I've still got some more nucleophile around. Should I do the reaction again? So notice what I've tagged these steps as. The first one, the nucleophile going in, the pi bond breaking and those electrons going up, the in-up part of this reaction. If Q can leave, if it's one of those groups, it's not carbon or hydrogen, then the electrons can pop right back down and Q can go out. So this is the down-out portion of the reaction. So the in-up, down-out reaction. And then you have to judge whether or not this reaction could happen again for another in-up. And you form yet another tetrahedral intermediate. At this point, if everything you have is carbons and hydrogens, well, then you just work it up with some acid-base chemistry and you're done. Okay? If Q was not something that could leave, if Q was a carbon or hydrogen, what you're going to see is that you're stuck right at the beginning and you just have to finish out with some acid-base chemistry. And I can give you some examples of those in the future. So really the unknowns that we're going to be looking at here are the strengths of different nucleophiles. We're going to see that strong nucleophiles tend to be ionic. No big surprise, right? Strongly negative species. An example could be sodium hydroxide as an example. Weak nucleophiles might be something like water or ethanol. I hope you see that this trend is very similar, right, to what we saw for SN1 and SN2. Electrophiles. Well, we've already seen alkyl halides act as electrophiles. The carbon bearing the bromine is electropositive. But now we have carbonyls that are strong, very electropositive, and we also have a bunch of carbonyls that are weaker, like carboxylic acids, esters, amides. To name those three. I could probably add aldehydes and ketones over on this side of the strong, but I'm not going to be talking about those in this chapter, so let's just take them out right now. But all of these have an electrophilic carbon that can be attacked by a nucleophile. Okay, so these are the things that we're going to be joining together to talk about this overall mechanism, the 1,2 substitution reaction. Now, before we get started on those reactions, those individual reactions, I also want to do a brief introduction to oxidation reduction. Now, oxidation reduction is a little different than when we talk about it in general chemistry. You guys memorize the Leo says grr, loss of electrons is oxidation and reduction, right? And so that is a little tougher to translate when you're looking at a carbon-based species. So I've written out the oxidation reduction ladder, which you probably will use a lot more in, your biochemistry courses. If you read what I've written here for oxidation, oxidation is the loss of carbon-hydrogen bonds and typically the gain of oxygen bonds. Okay, so let's take a look. If I started way down at the bottom here with an alkane, let's just look at this alkane. If an alkane, by some chemistry, converted, what chemistry do we know to form an alkene? That's elimination chemistry, right? Or perhaps we had to do a radical reaction to put a bromine onto the alkane, and then we could do our elimination reaction. Going from an alkane to an alkene is in fact an oxidation step in this ladder. We went from a fully saturated 3-carbon system to an unsaturated system. So technically we've lost carbon-hydrogen bonds, right? We had way more carbon-hydrogen bonds for the alkane than we did for the alkene. We had to lose some to make that pi bond. Okay, so we've definitely, going up this way, we've lost CH bonds. So that's oxidation. If you're adding carbon-oxygen bonds, it's so much easier to see and then thus define something as oxidized. So going from this alkene up the next rung to the alcohol, well, that's definitely oxidation, because now I have one CO bond. Going down, I have 0 CO bonds. Going from an alcohol to the alkene, I've decreased the number of CO bonds there. That's reduction. Reduction is the gain of CH bonds and typically the loss of CO bonds. So you kind of have to look at the plus minus, the gain loss of carbon oxygen and carbon hydrogen. If I go from an alcohol up to the aldehyde, I now have 2 carbon oxygen bonds, right? Because it's a double bond. So I have 2 CO bonds. If I go from an aldehyde to a carboxylic acid, I have the 2 CO bonds of the carbonyl and then 1 more CO bond. In the other direction, I have 3 CO bonds. So you can see that the climb from alkane to alkene, I lost CHs, but then I went 1 more up. I gained a CO, I gained 1 more CO bond at each rung of the ladder. And going down, you can see reduction goes from 3 to 2, 2 to 1, CO, and then I lose CO altogether with a double bond, and then I lose even more by gaining CH bonds. So this is a general trend that you can apply so that when you're in biochemistry and someone says this molecule gets oxidized, you'll see, and we see this a lot, an alkane will go to an alkene and they'll use the term oxidation and you'll go, what? What's going on? And this ladder can help you identify. We're not going to see oxidations in this chapter. Oxidation I will save for a future chapter to learn about. But we will see reductions in this chapter. We may go from a carboxylic acid all the way down to an alcohol, okay? Most of the reactions you're going to see in this chapter, however, are not reductions or oxidations, but derivatives. So we're going to go from, say, a carboxylic acid to an ester. Notice that they have the same number of carbon-oxygen bonds, and we didn't lose or gain any CH bonds in the process. So we're making lateral moves. So these are the derivatives of carboxylic acid.